In this problem, we have a piston cylinder device. Initially contains 40 liters of saturated liquid refrigerant. Okay, it's important. It's stated saturated liquid, so which means that we have to interpret this as x1 is equal to 0. The piston can move freely without friction. You translate this as constant pressure. Okay, so which means it's an isobaric process. And its mass is such that it maintains a pressure of 500 kilopascals on the refrigerant. So during all this process, the pressure should remain constant at 500 kilopascals. The question is the following: what is the resulting work if the refrigerant is heated to a final temperature of 70 degrees C? Okay, and we have to calculate the work, in this case in kilojoules. Since we have to calculate the work in kilojoules, so we have to remember that somewhere actually we'll have to calculate the mass, because we don't have the mass in the problem statement. Okay, so this will be problem 4.4. Business as usual, we will sketch our problem with state 1. What do we have? State 1, we have a piston cylinder assembly. We have here our refrigerant. So this is, as a refrigerant, this is the R132A, if I remember well. Yes, it's the case. So, and what do we have? We have V1 is equal to 40 liters. We don't like liters actually in thermodynamics, so this will be 004 cubic meters. We are told that this is saturated liquid, x1 is equal to 0, and we are given the initial pressure of 500 kilopascals. We are heating this gas, so we are adding heat. Okay, and this will lead us to state 2. And state 2, the piston will move up. Piston moving up means for us that a change in volume, dV positive, so we anticipate that the work will be positive in this case. Okay, we have this, we have our refrigerant 132A, and we are told that the temperature T2 here is equal to 70 degrees C, and we are told that the pressure will remain constant. P2 is equal to P1 is equal to 500 kilopascals. Okay, so which means that this process here is isobaric. P is equal constant. What we need to do, we need to calculate the work, so computation of the work 1, 2, and this will be in kilojoules. Okay, so we'll have to get the mass somewhere. So as usual, so we know that the work in a piston cylinder assembly like this, so it's work 1 and 2 is equal to the integral 1 to 2 of P dV. Is P constant between 1 and 2? Yes, it is, because the process is isobaric. So this will give us simply P1 integral 1 to 2 of P dV. Oops, sorry. Of dV, which is equal to what? It's equal to P1 cross V2 minus V1. Okay. So, and it's equal actually because we don't get the value, the values for the volumes on the table. So it's more natural for us to write it. Okay, it's M P1 specific volume V2 minus specific volume V1. Why I'm writing it this way? Because I know that I can get V1 and V2 from the table, the specific volumes, right? Not the volumes. So let's calculate in this case the mass. So we know that by definition, So our specific volume V1 is equal V1, the volume that's given, over the mass. So this is equivalent to say that the mass is equal to what? Is equal V1 over specific volume V1. Can we get the specific volume V1? Yes, because we have two independent intensive properties here. We have the quality and we have the pressure. So this means that V1 will end up being VF at 500 kilopascal. So with V1 is equal to what? Is equal to specific volume under the following conditions. X1 is equal 0 and P1 is equal 500 kilopascals, okay? And you will get a value of 0.00856 cubic meters per kilograms, okay? And you will get the value from this table here. So now we plug our value of V1 here. We know that the volume V1 is 004 cubic meters. So our mass M is equal to, we said, V1 over specific volume V1. And this will give us 0.04 over 0.308056. And this would give us a mass of 49.7 kilograms of refrigerant in our system. So is it done? No, because we just got this one. We just got this one. We still need V2, okay? If we get specific volume V2, so done deal, okay? I will just write it here. So, and what do we know? We know that V2 is equal to the specific volume under the following conditions. T2 is equal 70 degrees C, and P2 is equal to 500 kilopascals. So when you go to the table, be careful, go to the refrigerant actually table, you will find that state 2 is superheated vapor. So therefore you move to the superheated table for the refrigerant, and then you will get a value for V2 is equal to 0.05240 cubic meters per kilograms. So we're almost there. We have M, we have P1. We just now calculated V2, or got V2, sorry, from the table. We got V1, so we just have to plug everything here. So then we can calculate the work 1-2 is equal to what? Is equal M P1 V2 minus V1. And this is equal to what? Our mass is here. So this is 49.7. Cross P1. P1 is 500 kilopascals. Cross V2 that we just calculated or got from the table, 0.05240, right? Minus V1, 0.308056. And this will give us a value for the work equal to 1,282 kilojoules. And you say again that this is positive. It makes sense. There is a change in volume which is positive. dV is positive. The work is positive. The piston is moving up due to the heat. So therefore, our work is a work out and it's positive.